Hello everyone, welcome to another lecture on carbohydrate. In this lecture, we discussing the ring structure of carbohydrate, that are the monosaccharides. In the last lecture, we discussed the open chain structure of monosaccharide, but such open chain structure of monosaccharide has some defects, and these defects are helpful to give the evidence in support of ring structure of monosaccharides. The open chain structure of monosaccharide in the form of polyhydroxy aldehyde, for example glucose, fail to explain certain characteristic reactions of carbonyl group of aldehyde and certain other properties also. For example, glucose do not form the bisulfate compound. So when the aldehydic group or the ketonic group, when treated with sodium bisulfate, the addition reaction will be takes place and the bisulfate addition product is obtained. And this formation of the bisulfate addition product, it is a characteristic test of the carbonyl group. But in case of glucose, so when glucose is treated with the sodium bisulfate, then there is no addition of the sodium bisulfate across the carbonyl group of aldehyde. So this indicate that the D-glucose structure is not true open chain structure. The another characteristic test of the aldehyde is restoring the pink or magenta color of the cheap reagent. So when normal aldehyde is treated with the cheap reagent, then there is a restoring of either pink color or magenta color. The restoring of the magenta or pink color indicate that the aldehyde group is present. But when the D-glucose is treated with the cheap reagent, there is no restoring of the pink or magenta color. So this is one of the defect in the characteristic property of aldehyde group. The another is the glucose shows property known as mutarotation. In case of normal aldehyde or normal ketone, generally they do not show the mutarotation property, but glucose show the mutarotation property. When glucose is recrystallized from water below 50 degrees Celsius, and when again this dissolve in water, and if you record the specific rotation of the glucose crystal, it is near about the plus 113 degrees Celsius, which is fall gradually and attain the constant value of plus 52.5 degrees. Similarly, when we can again crystallize the glucose from water above 95 degrees Celsius, and again these crystals dissolve in water, and when you record the specific rotation, then the specific rotation is obtained plus 90 degree, which is standing gradually increases to a constant value of plus 52.5 degree range. So this clearly indicates that the D-glucose exists in two isomeric forms which cannot be explained by the open chain structure. Normally, aldehydic compound react with 2 moles of methanol containing HCl to formation of dimethyl acetyl compound. So when normal aldehyde treated with methanol, so 2 moles of methanol react with 1 mole of aldehyde to formation of dimethyl acetyl. But when the glucose is treated with methanol, only 1 mole of methanol is reacted with glucose in presence of dry HCl to formation of two crystalline isomeric methyl glycosides. So when D-glucose is treated with methanol in dry HCl, 1 mole of methanol react with 1 mole of D-glucose to use two crystalline isomeric methyl glycoside. So the presence of two such isomeric glycosides cannot be explained by open chain structure of glucose. In case of the glycoside and pentacetyl as well as the pentamethyl glucose do not show the carbonyl properties and mutarotation. So generally, if you see the structure of pentaacetyl, so the pentacetyl compound is formed by when the D-glucose is treated with acetic anhydride. So D-glucose having the 5 OH group. So each OH group undergoes the acylation reaction at oxygen atom to give pentaacetate compound or pentaacetyl compound. So in this pentaacetyl compound, we observe that the aldehyde group is 3. Similarly, when the D-glucose is treated with methanol, sorry, it is not treated with methanol. When the D-glucose is treated with dimethyl sulfoxide, then methylation is takes place on the OH group. So again, D-glucose having 5 OH group. So each OH group undergo the methylation to give pentamethyl glucose. So in this, the glycoside methyl pentaacetyl and methyl pentaglucose molecule, the aldehyde group is free, and we can expect that this aldehyde group show the characteristic test of aldehyde like bisulfate addition or restoring the magenta or pink color of cheap reagent. But these properties do not obey by glycosides, pentaacetyl or pentamethyl glucose. Also, this molecule show the mutarotation. So this mutarotation property we cannot explain with the help of the open chain structure, and therefore we can conclude that there are some defect in the open chain structure of the glucose. Similar to the monosaccharide of aldose, the open chain structure of monosaccharide also exists in the form of polyhydroxyketones, known as the ketones. For example, D-fructose. So these open chain structures are also unable to explain the certain properties of the normal ketone compounds. For example, the fructose does not form the bisulfate compound. So generally in case of fructose has the carbonyl group at the C2 position, and still the fructose do not show the addition compound. When treated with the bisulfate compound, that indicate that there is a defect in the open chain structure of fructose. Similarly, the deep fructose show the meta-rotation. When the deep fructose is crystallized from cold water below 50 degrees Celsius, and again this crystal dissolve in aqueous solution, and if you record the specific rotation of this solution is obtained, that is minus 20 degree. On standing, this meta rotates downward, still the specific rotation is minus 92.5 degree, which remains constant. Similarly, on other hand, again we can recrystallize deep fructose from hot water or hot pyridine above 98 degrees Celsius, and again crystallize deep fructose dissolve in aqueous solution and has a specific rotation of minus 133 degree, and on standing this meta rotate upward, still its specific rotation is minus 92.4 degree, which remains constant. Generally the specific rotation value is higher, is known as beta D fructose, whereas lower specific rotation is known as alpha D fructose molecule. So this meta-rotation property cannot explain with the help of the open chain structure. Like glycosides, fructosides and your monomethyl glycosides also do not exhibit the phenomena of meta-rotation. Normally ketones, when react with the methanol in presence of acid, gives ketone, and the ratio of ketone with methanol is 1:2. But when fructose react with the methanol, then ratio of the fructose to methanol is 1:1. And in this reaction there is formation of two isomeric compound called as methyl fructosides. So this is also cannot explain by the open chain structure, and therefore open chain structure are not suitable for carbohydrates, that indicate that the monosaccharides or carbohydrates have some distinguishable structure, or it may be the ring structure. Thank you to